All right, perfect. Sorry for the bloopers. I think they're a necessary part of presentations, and it takes many PhDs to still get to present in the right way. I'm going to go super fast. I apologize for that. We've been running short on time. So a quick overview. I'm covering self-supervised learning with transformers and how that's being used in MONAI, and we're trying our best to make it available. We believe in what Stephen Aylward was previously talking about this morning. He was making it, research should be reproducible. It should be usable. And if it's not being used, what's the point of it, right? So our first goal with self-supervised learning is create models that are big, which can be used by the community, researchers, scientists, clinicians to initialize on their tasks, and they can use them. So let's start with a quick intro on self-supervised learning and transformers, and then we'll take a look at the research timeline and then how you can access these resources with MONAI. So what is self-supervised learning? 10 years ago, when all of this really started, we were just looking at a lot of supervised tasks, and that just makes things very rigid. You're just saying, hey, MNIST data can be classified 0 to 9. And that's a very, very fixed perspective, kind of like mathematics, even though deep learning is defined by mathematics. But, self-supervised learning gives you a lot more flexibility, because over here, you can actually ignore the annotations, even if you have them, or you can also start creating your own pretext tasks and give perspective on the data. So I repeat, over here, the data becomes the teacher. In supervised learning, you were always focused on the task and the label is the teacher. But with self-supervised, you can just give the model a lot more context, and that's important. So a good example of that is over here. You can see augmentations. We've got out, cut out, in, cut out. What that means is that, you take a look at a patch and you keep that patch and you drop everything else out. Replace it with noise or keep it, black or 0. That's up to you. And that becomes like an augmentation. You can ask the network to reconstruct it. Now the network is just going to learn new things about the data because the possibilities are infinite. And this is just one perspective. Now think about, you can create many other tasks. For example, you started creating associations with text. So that's self-supervised learning. Moving on, what are transformers? Everybody knows here, like ChatGPT is great. Transformers are the backbone for these huge ChatGPT-like models. And in the computer vision community, VIT, the vision transformer, was one of the first ones that was created for computer vision tasks. The unique thing about it is that the image gets broken up into tokens, and those tokens are a linear projection of flattened patches. Now, because you have the patches along the length, you can still make connections because it's all going into a dense layer, and that allows for long-range dependencies where the convolutions are limited. And so that's where the transformers are really useful. I think that we have not figured out the right way to use the transformers with the imaging yet, but we're getting there. Every day is one step ahead. So here's the research timeline. I think one of the most popular transformer models out there is UNetter, and we came up with that in 2021. It's fairly popular, very easy to use. We came up with it, and then we quickly released it, and we realized, how often it was being used. And with this also, I'm just showing the way we like to do research. We find something useful, we put it in MONAI, and just use it, build on top of it. That's what I think will enrich the growth in this community, and we get to do newer, better things. After pursuing a little bit of transformers, we pushed into the self-supervised pre-training, and then further launched new transformer architectures, going from SwinUnetter into SwinUnetter version 2, etc. So let's take a look at how UNetter looked like. It was a simple architecture which took 3D image volumes as patches, and then you could project it onto linear dense layer, and that would go into the encoder, and then you follow it up with a decoder. It's probably, of course, not the best way, but it's a good start. And it became very popular very quickly, and it's still a pretty good solid baseline that's being used today. So with self-supervised learning, we experimented quite a lot of things there because it's very interesting. For example, I initially showed the augmentation. Now that's just one thing. I was earlier mentioning that you can give a lot of perspective with self-supervised learning because you've got many different kinds of tasks. And so our key takeaway from this work was that if you use many different pretext tasks, the model gets better. And that's what we found and published. This is also, again, out there and available for use. Our latest venture, this is still under submission, is how do you actually improve the self-supervised learning? So I want to draw quick attention to this figure right in the center. One really popular approach out there was the masked autoencoders. And their idea was like kind of advanced in painting. So when the model is masked out and it tries to reconstruct, you will see that it's missing out on the finer structures. And even if you look over here, the finer structure is missing at the top row. And so these are all small, tiny things, but they are very important for the images. And we call these the finer features of the 3D images. And so we started thinking deeper. How can we get the model to, focus more on these smaller, finer features? And so what we came up with was that if you look into low-level tasks, such as denoising or downsampling, then you can actually leverage more context of the data to the model, and that increases the model's performance. So we trained a bigger self-supervised learning, this time using 10,000 volumes with CT and MR both, and we found good results. And we were also able to overcome the masked autoencoder approach, which is quite popular in the computer vision community, but we haven't found it to be useful in medical imaging because medical imaging is special. It requires different kind of attention, and it's not like you can take computer vision concept and then directly apply it to medical imaging. It's not like that. You need to make it domain specific, and then things start working. We're going to be releasing code for this pretty soon. It's going to come up. Moving on, here is Swin Unitor version v2. This is already available with MONAI. The Swin Unitor is a switching window transformer network, and that for the first version, it was just a transformer, and we were just thinking about dense layers. But then we realized that overall, if you added convolutional attention to it, it actually helps the transformer, especially for the medical imaging community, because just with transformers, I mean, there are a lot of papers out there, and just being very honest, like everybody says, transformers are working great, but at the same time, the researcher is actually having a hard time, how do you beat these convolutional performance? So we found this, that, it increases performance. And again, this is available for use. Now, I've mentioned, a bunch of papers and everything. I just briefly touch base on how to use self-supervised learning and transformers with MONAI. So, it went too fast. Yeah, we recently pre-trained a Swin Unitor backbone with 50,000 3D volumes. On the left-hand side, you can see all the open source data sets that we've released. Of course, these slides will be released, and it will be, so you can check out these links yourself. We tried to cover as many organs as possible. There's also a guided tutorial just using the Beyond the Cranial Wall challenge to use these pre-trained weights via self-supervised learning. I encourage you all to try it, and if you break it, please reach out. We'd be happy to improve it and provide more support. Then there are also all of these transformer networks available. I put the links, and then there's the self-supervised learning tutorial and weights as well for both Unitor, Swin Unitor, and we'll keep pushing on the transformers. With that, I'd like to quickly end, and we'll take questions at the end. Thank you, everybody. I'm gonna stop my screen share. Dr. Yang, take it away.
Okay, thank you, Dr. Nath. Let me share my screen. Here's my screen.
Yeah, we can see it.
Perfect. One second. Okay. Hi everyone. Today I'm going to briefly introduce the feature in MONAI we call Auto3D segmentation, Auto3DSeg. And so this feature has been released for quite a while, almost a year. So during this recent release of MONAI, we have incorporated a lot of new features into this pipeline and to make the entire pipeline more robust with better accuracy. So for those who are not familiar with Auto3D or in general segmentation, so segmentation is kind of a very popular topic in the field of the medical image analysis. So this is if you take the keywords of the MICAI, for your information, MICAI is the largest conference in medical image computing. So if you just take a keyword of MICAI for 2021, so you can see the most popular word is segmentation, deep learning. So again, we do the same for the year 2022. You can also see several of most popular words are segmentation, deep learning, and image. So as you can see, the segmentation is a very, very popular task. I assume a lot of you are familiar with this task. So basically, the given 3D volumes like the CT, MRI, and we are trying to extract 3D structures of organs or tumors or bones. Here are some examples of a heart segmentation from MRI or liver and tumor segmentation from 3D CT. So in general, the plain model training is quite straightforward, but our question is is it good enough? So our thinking is it is the plain model training is good for demo purposes of tutorials for beginner to understand what's the logic behind. But if you want to publish a paper or participate in any public challenge, so which can be insufficient. So our goal of Auto3DSeg is to provide world-class experience of 3D medical image segmentation with minimum or no user interaction. So we are aiming to provide effective models with decent efficiency, and we are trying to accommodate a lot of scenarios meeting different user needs. So in general, the Auto3D is kind of a feature, quite a powerful feature in MONAI's self-contained solution to build 3D segmentation model with minimal or no user input. So currently we provide several algorithms swing unit R, as Vish just introduced, and the things which is a work of neural architecture search, also published in CVPR, and also another popular work, SegResNet. So we're actually running all of those algorithms, and we are trying for different tasks. We are trying to figure out what's the best combination of these three algorithms. And also the entire pipeline trying to build for high accuracy and efficiency 3D solutions. And also from the left-hand side figure, you can see, so originally if you start from everything from scratch for segmentation task, normally you need to probably write hundreds of thousand lines of code to develop the pipeline for specific task, and you need to tune the parameters and a lot of stuff you need to do. But if you incorporate this feature into your workflow, you only need to, from the high level usage, so you only need to use a code 1 to 5 lines of code, and let the model GPU running for a couple of days, here the 2 days for breast 19, I believe, and then you will give you state of solutions for that data set. So that's kind of experience we want to provide for users. And also, in order to validate the effectiveness of the Auto3DSeg, we actually use this solution to participate in several challenges last year's MICAI. So the solution won the first place in Hector 22, which head and neck segmentation, and in general second place in instance 22, and the second place in ISLIS 22. So and also, if we only compare the dice score, actually our solution reached the top dice score for all the 3 tasks. So in general, here's a big picture of Auto3DSeg. So we have 2 phases. Like first phase, the training phase, we have like a different components. For example, here we show like a data analysis, like we select algorithms, and we generate algorithm based on different data set and data statistics, and we do the model training and the option. We can also have the optional hyperparameter optimization. Then based on the training result, we rank the algorithm and choose the best one. Then we in the inference phase, you can apply this like a trained model, like to generate the segmentation for the task with like either a single model or the model ensemble of several algorithms. So it is a unified framework and very flexible modular design. And also we kind of support like customized algorithm. And again, we validate the pipeline with like a state-of-the-art performance. So so in the tutorial we have also the notebook you have on your side, we provide some quick example, a real world example, and you can get a feeling about the different command or different steps of the entire pipeline. Yeah, so basically, if you have the high-level API, we call using high-level API, we call it auto runner. You just need to provide 3 lines of code, like, so what's the modality you're using, what's the data list you're going to have. Like basically, data list means you need to provide correspondence between image and the label, and also you need to let the auto runner know where your data is. So once all this information are provided, then you can run the following lines, so just 1 line of code and kick off the entire process. So you will figure out how many per GPU you will have, how much memory of your GPU, and figure out everything and customize the hyperparameters for the entire pipeline. Okay, here's a multiple different. Also, you can run the different steps like 1 by 1. For example, if you want to run the data analysis, so you can just call the data analyzer. There will be more in the new notebook or in our official tutorial in MONAI tutorials. So for this recent release, we actually update a few things. Like we are trying to improve the performance. In terms of performance, we are trying to improve the model training efficiency and the GPU utilization rate and memory footprint, and also robustness to GPU out of memory. So again, so there's like basically 3 or 4 algorithms we provide here. You can see segresonate 2D things, and swing unit R. So we also did a lot of improvement in MONAI and also fixed several bugs. So we use this challenging data set, which is quite popular recently. It's called total segmentator. So which contains like a more than 1,000 CT images, like the whole body CT. They provide an annotation of organs, bones, and other vessels. You can see from this figure. And so we follow the common practice to train a model for 18 classes, because like they provided this, the work they did, they train a model, they train 5 models to cover 104 classes in total. So each model will take care of like 18 classes. In order to make a fair comparison, we train the model with 18 class of the 104 classes. So we compare the training time and the GPU utilization rate. So here you can see the benchmark we have been done is using A100 GPU with 80 GB memory. So basically you can see we run the experiment with 1 GPU, 8 GPU, 16 GPU, and 32 GPU. So with more GPU, you can see the training time will be significantly reduced. And if you're using like a 32 GB GPU for model training, which are 4 nodes, so you can see the training time of each algorithm could be quite efficient. And another feature we're trying to improve is like sliding window inference. Because like sometimes the 3D volume is very large. It's hard to do the straightforward inference with entire 3D volumes. That's why we So the sliding window inferrer is kind of a common practice in the modern 3D image segmentation pipelines. So, but there's there's some overhead. So because like if you want to do the sliding window to inference, you need to decide you want to do the you make prediction on the windows, but you need to stitch the prediction of windows together to form the prediction of the entire volume. So, but you need to decide that you want to stitch on GPU or on CPU. So basically, it's really tricky for users to decide based on their device. So, and we kind of like refactor this like a class implementation. You can see from the MONAI 1.1 to 1.2, we significantly reduced the stitching time on either CPU or GPU. And also we significantly reduced the GPU memory usage for this like entire sliding window inference part. So it's quite nice for users. So the buffer mode, here's the new mode, is kind of interesting. It's like buffer mode. Buffer mode means like we cannot do the entire sliding window inference fully on GPU. And the buffer mode will take part of the image. So this part of the image will do the inference on CPU, and another part, the rest will be on GPU, based on your available GPU memory. Then once the inference is done, we'll merge stitching the predictions together to form the entire segmentation mask. That is kind of quite nice. You can see like you can also reduce you can increase the inference time a little bit, but significantly reduce the memory usage, but still like much faster than fully stitching on CPU. And also furthermore, we provide this new class like sliding window infer adapt. So this one will automatically figure out which mode you need given the GPU memory budget. So basically the logic is you will try the GPU mode first. Then if not, you go into out of memory, then we will automatically switch to buffer mode. If the buffer mode is not possible, you will switch CPU mode. You will figure out by yourself. And also you will record the history of the inference. So the history can be used, can be applied for a new image. For example, in the future, if like it has some, you get the history, you will use the history of the information instead of trying off the 3 different modes. And also, yeah, another nice improvement we have made trying to reduce the memory footprint of the dice metric computation. So previously, computing dice of like of several classes, which normally will take a lot of memory, especially the memory consumption mostly from the one-hot encoding of ground truth label or prediction. So we actually improved this part. So originally, so for the last version of MONAI 1.1 dice computation, we will take overhead like 3.5 gigabytes, given a certain size of the image. Then in this new release, we kind of reduce the memory overhead like significantly, like only like 0.5 gigabyte. And also in all of our algorithms in Auto3DSeg, so we kind of doing like automatically GPU CPU switching when the your computation is out of GPU memory. So you don't need to worry about it. The entire pipeline or each algorithm will take care of it by itself. And there's a few other updates. And data analyzer. Previously, we have like a single GPU version. This release, we provide this like multi-GPU version, which is much faster. It could be used like a multi-GPU or multi-node. And now for the auto-runner improvement, this class, so let's see if the auto-runner has already trained some algorithms. So if we kind of keep the history, if you want to resume this like process, you can reuse the same command and skip the auto-runner will skip the algorithm which already trained. So, and also with this one, as you see in the benchmark, we provide nice multi-GPU or multi-node support. And so that's another quite important feature is like we're trying to improve the automated parameter selection for each algorithm. So in each algorithm, we call it auto scaling. Basically, it's basically given different GPU budget and CPU budget on your environment, in your environment. So the algorithm will automatically decide better resolution, what's the normalization strategy, the number epoch iteration choice, and also like a batch size or the window size. Everything will be, if you turn by default, the auto scaling feature is turned on. So if that's turned on, you will figure out everything by yourself automatically. You don't need to worry about it. And also in this new release, we kind of fixed a lot of bugs, several bugs, not bugs. And to be specific, we are for each algorithm we make additional improvements. So basically, segmentation 2D has been rewritten based on some like recent development, and Auto3D segmentation 3D model actually got improvement for non-isotropic resolution, which means the model can take will treat non-isotropic data differently. For example, the input CT resolution, let's say it's a 1x1x4. So the model will use like 2D model and combining 3D model in order to accommodate, let's say, like non-isotropic resolutions. And for things, so our colleagues and also and our team members all identify a few like issues with low GPU resolution utilization of previous implementation, especially in the forward operations. So we kind of refine the implementation. So now the GPU utilization tree can be improved by 30%. And the fourth, when you net R, so as Vish introduced, so we already incorporate the pre-trained weights from previous CVPR works into the current pipeline. So basically, when you run this algorithm, some algorithm will download the pre-trained weight first, and uses the pre-trained weight as a starting point and do the model training, which will significantly improve the training convergency. So in general, we are trying to improve the medical image segmentation pipeline in many aspects. We are trying to improve the accuracy, efficiency. Also, we want trying to improve the user experience. And yeah, we provide self features. We will like to have all of you to give a shot and to apply it in your own task and see and give us some feedbacks. So here are some related links about the Auto3DSeg. We have the app, it's a MONAI app, Auto3DSeg. And now we have the tutorial part. So it shows how you run it different as an entire pipeline or to run different modules. And also there's like a research contribution part. In the research contribution, actually, we provide we update the algorithm template there. So there's like a default template in the MONAI repository, but we are keep developing for the latest algorithm template there. So if you want to use the latest like algorithm template, you can check out the template in the research contribution. Okay, that'll be all for my presentation, and we will be happy to answer any question from your side. Thanks.
The MONAI Bootcamp link or repo is already in chat, but I'll go ahead and put it in one more time here really quickly. If you go to that repo, there are links if you scroll down here to the Auto3DSeg Hello World example. So it's a slightly different version that's in the normal Auto3DSeg example. But you can click on either Open in Colab, or if you sign up for Studio Lab, click on Studio Lab, and that'll take you to the page for going into the actual notebook. If you're using Studio Lab, you'll get dropped on a page like this. You can click Start your runtime, use a GPU, and then you can click Copy to Project. And what that'll do is that'll put you into a Jupyter Lab interface, and it'll ask you do you want to copy the file or do you want to copy the repo? either works. In this case, I only copied the file here. And so this is a file here walking through Auto3DSeg and a lot of, again, what already Dong talked about. So I'm going to go through this fairly quickly here. Let me make this a little bit bigger for you guys. But the main idea is that we are going to walk through the basic setup of the hello world and using a not real world data set, but a synthetic data set, because that'll at least show you how it works. And it'll let you run through this example in about 2 minutes or so for the actual training part. And so to get it set up, we can verify that we are on a GPU by running NVIDIA SMI. In this case, we'll have to do some different imports and tests to make sure everything is installed. We want to make sure MONAI is installed. And then on SageMaker, there was a few other things needed. On Colab, there is less of a need for some of these installs. We make sure installs are there. And then we'll pull in the imports. So Dong already talked about auto runner. And then we're going to use a MONAI data function for create a test image 3D. And so if we go down, we'll see this JSON or this object, Python object that is going to be used for generating the synthetic data. So basically we have test set, training set, we indicate the number of folds we want to do for things, we give it the image and the label file that we want to use. And then what we're going to do is use this object to go through and iterate over in a loop and say, okay, go through, create this folder called Hello World Working Directory. We're going to read in the data list. We're going to make sure that the path exists and that we're going to use the create test image 3D function here to create based off of the different class names and the dimensions that we indicated up above. And in this case, it would be 64 by 64 by 64. And then we'll save that out to the folder. And so then we will have a Hello World directory that has all of the different files that are in it that we want to use for this for synthetic data. We can look at it really quickly here. And so it just looks like this in a 3D volume. We took a different slice of it just to see an example of what it did look like. And so you have the label and the image, and we'll use that as the basis for the training that we're going to do. So again, this is where Dong really talked about the workflow for Auto3DSeg. And in this case, there's the auto runner here. And so really all we need to do here is we say the modality, in this case, we indicate is MRI. We give it a working directory where all the files are. We pass in the data root directory, which we had up above, which is Hello World Working Directory. And then the data list, which we also had up above of the different files that we have in testing and for training and the different folds for everything. So all of that is already contained in everything that was up above. And now we call it to the outer runner, we instantiate it, and then we're ready to run it. And so before we run it, we want to make sure to set a few different parameters. And in this case, because we want to run it fairly quickly, we say number of epochs, number of images per batch. Do we want warm up? And we have those fairly low at 1 or 2 for these different ones for this run. And we only say 1 fold as well for the number of folds we want to run through things. And so after we set those parameters, all we need to do is call run on the runner object from up above. It has those parameters set, and it'll go through and work through all those different pipelines, and then it'll give a result at the very end of it. So it'll ensemble at the very end. You can see here that it says it picked the following network to ensemble, our SWIN UNetter 0-fold network. And now it's going to use that for the final predictions. And so we can go through and say, here are the different test image. Here's a test image. Here's the ensemble output image path that we have for everything at the very end, the predict on. And then we can read that in and look at the background, both ground truth and foreground ground truth, and then the background prediction and the foreground prediction. And you can see that there is a little deviation on the bottom circles in particular, that the edges aren't as clean as the actual the ground truth, but we only trained for 1 or 2 epochs. We didn't train very much on it, although the data is fairly simple. And this took about 2 minutes where it'll load the data, go through each of the networks, run the different folds, run with the parameters, and then ensemble and give the results back. And then you can test it out pretty easily. So if you were to increase those numbers to 5, you probably would have it perfectly matching the ground truth for the prediction. But it kind of walks through the general workflow for it. And in this notebook in particular, and why it's different than the original notebook, is we also have some additional optional exercises here. And this is where you kind of can play around with what you want to experiment with, the different algorithms that are in there. So you can shorten it and say only do 1 or 2 algorithms. You can expand on the dense search and train phase for it and pass in different parameters for that. You could bring in a real world data set. There is a MSD_data list generator Python notebook in the tutorials repo that pulls in segmentation decathlon data sets. And we have a wrapper in MONAI that can easily pull it in, generates the data list for you based off of it automatically, and then we'll pass in everything into the auto runner. So almost exactly what's up above, except for the data generation or data list generator piece is swapped in for this medical segmentation decathlon dataset version. And then it'll run exactly like it's running here. It won't take 2 minutes. It'll probably take 20 minutes, 30 minutes, an hour, depending on what GPU you're running it on. But very easy to swap in from synthetic toy data set to a real data set and actually trying it out. And then there are 2 other ones down here, which is hyperparameter optimization, which we don't have integrated right now into this Hello World example, but there are tutorials for both NNI and Optuna tutorials that you can integrate into it. And then you can also break down each piece of the pipeline within AutoRunner and look at what all those are calling out to. And so there's a notebook called the AutoRunner or Auto3DSeg AutoRunner Reference API notebook that will show you how to call to each of the internal API functions, because maybe you kind of want to split things up and pass them in individually and customize different functionality within those. And so you have a little bit more fine-grained control over that pipeline for things. So 4 other examples. So I encourage you run through the Hello World notebook and then look at the example and see how can I expand on it. And if you sign up for Studio Lab, you should continue to have access, but it is a 4-hour session that you have available. And I think same with Google Colab, there is a limit to the session length that you have. But go through and test it out, work through the notebook, try out some of the optional exercises and just kind of get a feel for it. And then if you get a chance, try it on something you're working on. If you have a data set, generate that data list and see what it looks like to pass it in and try a very simple, maybe few epoch version of Auto3DSeg on your own data.